Hey everyone. In this video, we're going to look at an alternate version of conservation of energy that is useful in certain cases. Now, I want to be really clear about something from the outset. What we're learning in this video is not new physics. Conservation of energy is still just conservation of energy. It's just a description about the way the world behaves. Energy cannot just appear and disappear. It has to go from one place to another. The equation for conservation of energy that we've been looking at in this course looks like this. This equation just says that the change in the total amount of energy in a substance is equal to the heat that is put into or out of the substance plus the work. Now, many problems involve situations where a system is closed. When a system is closed, we can say that a change in the total energy of the system is equal to zero. There's no heat or work. But it turns out that there's another way of writing this exact same thing. It looks like this. It says that the total energy in a system is constant. Now, this is exactly the same as what we've said before, but it turns out that there are some cases where this second way of writing conservation of energy is a lot more useful. In a system where energy is conserved, in other words, where the change in energy is equal to zero, this equation tells us that if we've determined how much energy the system has at one point in time, we've actually determined how much energy it has at all points in time. If we can determine how some of the energy systems are changing, we can determine how the other energy systems are changing just by requiring the fact that the total energy of our system is constant. Now, this might feel a little abstract as I'm describing it in words, so let's look at a really quick example. Let's go to the whiteboard. We're going to start here by looking at a problem that we definitely could solve using the other version of conservation of energy. It's just a ball dropping problem. In this case, we're being told that when the ball hits the ground, it has 50 joules of energy. What we want to know is how high the ball was dropped from. We're assuming that no energy is lost. In other words, this is a closed system. The nice thing about this is that because this is a closed system, our new version of energy conservation applies. If we can calculate the total energy at any one point, we've calculated it for all the other points as the ball falls. We can say that when the ball hits the ground, it has zero gravitational potential energy. And we also know its kinetic energy. So we know the total energy of the ball when it hits the ground. It's just zero potential energy plus 50 joules of kinetic energy. Now that we've determined this, we know how much energy the ball has at every moment between when it is dropped and it hits the ground. It's just 50 joules. So now let's look at when the person is holding the ball and about to drop it. We know that at the moment that the ball is dropped, it's not actually moving, so it has 0 joules of kinetic energy. But since the total energy has to be equal to 50 joules, we immediately know how much gravitational potential energy the ball has. It's just the 50 joules. So if the gravitational potential energy is equal to 50 joules, we can just write out the equation for gravitational potential energy and set it equal to 50 joules. And there we go. We've determined how high the ball was when it was dropped, just by noticing that the total energy in our system must be constant. Something I want to note here. Because this is just another way of working with conservation of energy, any problem that can be solved using these techniques can also be solved using energy interaction, at least in principle. But there are going to be cases where it's going to be a lot easier to solve things this way. Let's look at one such example. Here's an example of a problem that we can solve with this new version of conservation of energy. In this example, we have a block connected to a spring. The spring is going to be compressed and then released, launching the block to the right. As the block travels across the floor, it's going to experience friction. That friction is going to go into the thermal energy of the block. By the time the block reaches the end of the horizontal segment, its thermal energy will have increased by 20 joules. It's then going to go up this frictionless slant on the right-hand side. The question we want to ask is, what is the maximum height of the block on the slant? Now, this differs from other energy conservation problems in a key way, in that instead of being given the values of the indicators, we're actually being given the values of the energies at particular points in time. Now, we could use energy interaction in order to solve this problem, but it would be a little bit tricky because we don't know anything about any of the indicators in the system. So instead, let's just use our new model of conservation of energy. The first thing we want to identify is if there is a point in the process where we know what the total energy is. At the beginning of the problem, when the spring is compressed, we know how much spring potential energy the system has. It's labeled there. It's 75 joules. At the beginning of the problem, that's the only kind of energy that the block has. And so we know what the total energy of our system is. It's just 75 joules, the amount of energy that's stored in the spring at the beginning of the process. So let's write that down. Our total energy is equal to 75 joules. So what about when the block reaches its highest point? Well, we know that the spring mass potential energy doesn't exist anymore. The spring released all that energy when it launched the block. We also know that the kinetic energy of the block is 0. It's at its highest point, and so it's momentarily coming to a stop before turning around to slide back down the hill. We also know that the block has thermal energy. Specifically, it has 20 joules of thermal energy. This is just the amount of thermal energy that it gained as it traveled along the track. The only other kind of energy that the block can possibly have is gravitational potential energy. After all, it is moving up a slope, so its gravitational potential energy is increasing. How much does it have? Well, it just has 75 joules minus the 20 joules that is now in the thermal energy. There's no other kind of energy, and so we know that all of the rest must be in the gravitational potential energy. And there we go. We know how much gravitational potential energy the block has at the end of its run. So let's just compute what the height is if you have that much gravitational potential energy. Let's see if we can find a mass. Okay, it says the block has a mass of 3 kilograms, so we just plug that in. And now we just solved. And there's our answer. The maximum height above the ground that the block reaches is just 1.83 meters. Again, we just did this by noticing that we can determine the total energy at a particular point. Because we can model this as a closed system, finding the energy at the initial point means we found it for all the points, no matter where in the problem we go. For example, I could now ask you to compute the speed of the block at the moment that it reaches the hill. You could do this the exact same way. You know the block has 20 joules of thermal energy when it reaches the end of the flat part. The block has a total of 75 joules of energy, so we know that the remaining 55 must be in the kinetic energy. You could then just compute by using the kinetic energy equation the speed of the block. One of the nice things about this is it doesn't matter where in the process you can compute the total energy for. In our first example, we knew how much the total energy of the system was at the end of the process. In this example, we know what the total energy of the process is at the beginning. It's also possible you could be given a problem where it's somewhere in the middle that you know what the total energy is. You'll see one of those in DL. The point is that it doesn't matter. If you can compute the total energy of the system at one point, you know it at all other points, and you can use that information just like this. Now, of course, this still requires you to keep track of what kinds of energy are in your problem at any given time. But that's something that we know how to do. We've gotten a lot of practice in it. Now, you might have gotten to the end of this video and wondered why we introduced this. It doesn't really seem that we've learned anything new. But I promise that this version of conservation of energy will really start to come in handy, and we'll see why by the end of the week. That's all for this video. I'll see you in the next one.